Well, I'll just welcome everyone while we're getting that set up. Thank you all so much for coming. I know that with the pandemic and all, your busy schedules are probably even more hectic than usual. So we sincerely thank you for taking the time to be with us today. Daniel, do you need any assistance?
It's coming. Sorry, I just had it at the wrong place in the PowerPoint.
That's all right.
All right, should be good now.
All right, thank you. All right, so this is our capstone design presentation. Just a little background on the situation. Our partners were FRC East at Cherry Point. They acted as a company coming to us with a real problem, and we acted the part of a engineering consultancy firm that was going to solve their problem for them. For completeness sake, we chose a name for our company, Aerothermal Engineering Solutions. That's the logo you see on the left. Now, my name is Andrew Wilwarding, and I'm gonna let my team introduce themselves right now.
I'm Daniel Caldwell.
I'm Mike Crawford.
I'm Jason Denny.
I'm Austin Ehart.
I'm Nick Hickens. I'm Elijah Hayden.
I'm Tucker Mentink.
Gail Moffitt.
Leona Ritchie.
I'm Rogelio Velasquez.
I'm Michael Wood.
All right, thank you guys. Could I have the next slide, please? All right, so our agenda is pretty simple. I'm gonna go through the design process that we use. This is pretty unique to our program, so I'm gonna spend a little time there. And then some of the other team members will go through each subsystem of our system. And then finally, we'll close up with a cost estimate that'll give you a good idea of the scale of this project. Next slide. All right, so like I said, our program is a little bit unique. A traditional program, it's going to teach students how to dive into the technical depths of a design project. But ours, we start a semester earlier, so we can really get a good systems breadth added to it. So in other words, we're not going to miss the forest for the trees. Next slide, please. All right, so context is very important in the systems perspective. Like I said, the traditional design class is going to be a little different. They're going to have ready-made requirements that they're going to design to, whereas we had to start from the point the customer came to us with a problem. We had to develop those technical requirements ourselves and then design to them. So the context is very important in this process. And first of all, for those of you who do not know, FRC East, Fleet Readiness Center East, performs repair and overhaul of various aircraft for the Marine Corps and the Navy, like the CH-53 Echo you see in the right bottom. These get taken down all the way to the bone and rebuilt, and afterwards they need to be tested. This is very important for keeping these machines flying because they've been around sometimes for decades and will be for decades more. Next slide, please. So obviously very important to the aircraft is its engine or engines. FRC also does overhaul and repair of these. So once they have undergone the repair, they need to be tested. There are special facilities to test called test cells that you can see on the right there. And this is getting to where our design comes in. Next slide, please. So our design was to make a aerothermal test set, the purpose of which was to verify the airflow going through any given test set matched the characteristics of another standard test cell. In order to do this, we needed to acquire, display, and record live airflow data. And the most common method of doing this was to set up an array of sensors at the intake of the engine and then an array of sensors at the exhaust of the test cell. Next, please. So getting back to our process, the first phase, and one that was unique to our program, was called requirements definition. So this is where the customer gives us requirements. Very often they're vague. Sometimes they don't know exactly what they want themselves. So we have to put a lot of research and communication back and forth with the customer and other interested parties so we can produce technical requirements that we can design to. Next, please. So we came up with this needs statement, which kind of encapsulated these requirements. Once the requirements would be satisfied, this need should be satisfied as well. So it's simply provide FRC with complete designs for a configurable test kit that will gather, display, and store a combination of temperature, pressure, and velocity data for various indoor test cells for the purpose of test cell verification. So one of the great challenges for our design was that we didn't have one test cell that we were going to design for, but any given test cell from a certain smaller kind of test cell up to a larger one. And so we had to make our design configurable to do that for all the test cells. Next, please. So to keep us on track, we did a series of design reviews, starting with the systems requirements review. This is when we reviewed the requirements that we generated. The customer was there, as well as other technical representatives to look over our shoulder and just make sure that the requirements we produced would truly satisfy the need. Next came the concept review, and this was just when we started translating the requirements into how we were going to satisfy them, just a general concept. Next came preliminary design review. This is where we start digging into the details. Very often, about 85% of the details will be figured out by this time, followed by detailed design review. This is ideally when all the details will be worked out. Inevitably, some details will slip through, and so we have CDR, lastly, that will make sure that all of those get resolved. Next, please. Next slide, please. All right. So just to give an overview of our concept, we have a test cell in the middle here. We have air that comes in at the intake. Next, please. And it's going to go through the test cell, go down through the intake, through the engine, and up through the exhaust. So we split our system into two major systems. One were called the rakes, and the other was the data acquisition. So the rakes included the intake rake, next, and the exhaust rake. And again, these are the structures that hold the airflow data sensors in an array in front of the engine and then after the engine. Next came the data acquisition cases right here, and then each of these had to be powered. And then finally, we also produced the computer program that would process the data and display it and record it. Next, please. All right, so this is the system architecture that we came up with. We had 12 engineering students on the project, so we split 6 and 6, 6 on the rakes and 6 on the data acquisition. Then further, we separated into 2 smaller teams to tackle the intake rake, exhaust rake, case instruments, and the software. So that is all that I have. Now I'm going to hand it off to Jason Denny, who will go into the intake rake details.
All right, thank you for coming again to our presentation. Today I'm going to be rake. Next slide, please. So to the left, this is our final design. And the main purpose, as Andrew was saying earlier, is for this rake to be placed inside of a test cell and provide attachment points for the airflow measuring devices that will measure the intake flow for the engine test cells. This rake on the left is a single rake, and by design we have it to support either one or two masts, as you see there, to cover the flow that whatever's needed for whichever test cell it happens to be in. The picture on the right is just going to show the names of some key components as a reference for later when I'm going over the features. So hopefully you can remember them. I'm sorry we don't have a packet to hand out this time. The first is the carriage plate, and that is where the mast is going to connect to. And underneath it is a pillow block, and that's where the carriage plate will attach to. And the pillow blocks also are housing for linear bearings that will slide along the shafts that you see and also rotate as needed, which I'll go into a little later. And then the shaft supports that will connect the shaft to the base. And then, of course, the base is made up of two side legs and the two center beams. Next slide, please. So here, this is one of the first things that we did for our design, and it was to analyze the mast due to the force of the air coming through the test cell. And this is just an example to show you how we were able to use our technical skills that we learned throughout our engineering courses throughout this program. So I won't go into too much of the details, but what this allowed us to do was to determine the size of the pipe that we needed to attach the fixtures to the devices. And then with further calculations, we were able to determine the weld size that's going to connect the mast at the bottom. And then even further, we were able to determine the weight that we needed for the base to withstand any type of slipping or tipping over due to the air flow. And then another important part was determining the size of the base structure. Okay, here I'm just showing an intake rake again inside of a particular test cell. It's in the blue rectangle, and showing the airflow direction. It's coming through the top in this particular case, and then it is going through the test cell, and it passes our rake structure to collect the data that we'll need. Next slide. Okay, this just shows a closer view of the rake inside the test cell, so you can get a better visual of the airflow coming through from the left across our instruments, and then through the test engine intake, and then out the exhaust. Next slide. And here I am showing the clamp that attaches to the mast, and there's a plate in front of the mast, and we manufactured that and designed that to hold the two instruments that you see there. And one is a thermocouple, and what that does is measures the temperature of the airflow as it's coming through. And then there's a pedostatic tube, and this is used to measure the pressure, and also it allows the DAC team to do a calculation that will determine the airflow as it's coming through. Next slide. Okay, and as we were saying before, that these are rakes that have to go into many different size test cells. So this is showing 5 rakes, excuse me, put together. And this was part of the design too, to meet the requirement of our spacing. A single rake with 2 masts will cover the minimum envelope airflow of 23 foot high and 5 foot wide. And then we have a maximum size envelope of 32 feet high and 24 feet wide. Next slide. So now I'm going to go over the key features of our design. So after the base is assembled inside the test cell, the mast that we have is able to lay down on the ground, and this will allow the operator or whoever's putting it together to attach the instruments along the mast. And they can attach these anywhere along the mast except for the coupling places and the place where the brace support will attach, which was not an issue for us. So that covers our requirement for our vertical spacing, which was 2 feet and adjustable up to 4 feet. And then after the next slide. The last key feature of our design was the masts are able to slide horizontally to the left and to the right. And this allowed us to cover and meet the requirement for our horizontal spacing, which was 3 feet to 5 feet. And next slide. Here I'm just showing one more time a picture of multiple rakes, and this will give you an idea of our largest test cell that it'll go into, which is 5 rakes together is about 22 feet wide, and then with the 3 masts up, it goes up to the 24-foot high height that we needed to do to meet the requirements. And that's all I have for our intake rake. Then I'll hand it over to Michael Wood for the exhaust team.
Hello, my name is Michael Wood. I worked on the exhaust rake with Roy Velasquez, Tucker Mentink, and Caitlin Moffitt. Today I'm going to show you the exhaust rake design and some of our key features and key components. Next slide. So during test cell verification, we'll have 2 rakes running, the intake rake, as you saw before, and then the exhaust rake will be on the top of the exhaust stack, and as you see circled in red to your right. Next slide. So our exhaust rake had to be configurable to different test cells of varying sizes, so we used sections of cross members and I-beams to allow it to be adjustable to the application. This assembly shows the configuration. This assembly shows the configuration for the largest of the test cells, the F402 at Cherry Point, which had an exhaust area of 31 by 31 feet. And this rake is made up of 12 I-beams and 14 rectangular cross members. Next slide. This design configuration is able to be configured to different test cells using the same components. This configuration would be the smallest we would use for the T700 TurboSaf test cell, which had an exhaust area of 6 feet by 6 feet. It only uses 2 I-beams and 2 rectangular cross members. Next slide. So in order to configure our design to different test cells and our spacing, we had holes drilled every 3 inches along our cross members and every 4 inches along our I-beams. So our design had to have strong end-to-end I-beam connections that would handle the stresses produced during the operation of the test cell and during lifting of the structure onto the exhaust stack from the ground. This area of the design required many iterations of strength calculations and adjustments to the design in order to ensure that the final design would be structurally sound during test cell verification and during lifting. Next. This slide shows how our instrument fixtures are attached to the cross members, and they can be moved every 3 inches. We have hole spacing along our cross members every 4 inches and every 3 inches along our I-beams, which allows a lot of adjustability in the configuration of the rake, as well as a location of the temperature and pressure sensors. This is our instrument fixture. It will connect the pitot-static tubes and thermocouple probes to the structure. And then the hoses will be routed from these instruments through this U channel along the top of the cross member out to the edge of the rake and then on to the data acquisition cases. Next slide. We used a custom clamp that was machined and a Hilti anchor bolt at a depth of 4.5 inches in order to hold the whole rake structure onto the exhaust stack during operation so that it doesn't fly away from the drag forces produced by the exhaust of the engine. We also chose 10,000-pound capacity steel hoist rings that will be used to lift the rake from the ground, and a custom connection plate that would be machined to connect these hoist rings to the I-beam. That's all I have for the exhaust rake, and at this point I'm going to turn it over to Daniel to talk about the data acquisition cases.
Hi, my name is Daniel Caldwell, and myself, along with Liana Ritchie, Nick Hickens, and Mike Crawford, all worked on the data acquisition hardware kit. And I just want to start off by telling you all how proud I am of the product that we were able to customer. You know, our customer had some negative experience in the past with this type of test equipment, and they came to us expecting something much better. It's one thing to take a lot of, sensors and modules and power supply, get all the right equipment together, connect all your wires and hoses, and just collect good data. But then to take all of those components and package them into a compact, portable, rugged case and still provide an exceptional user experience as far as getting your hands in there and working on things, that required us to look at data acquisition hardware from the ground up. Every inch of our design has been looked over with the customer in mind. We thought about every single wire, hose, and cable, where it needed to go, and made sure that we provided a clear and organized way for it to get there. Then we carefully selected the right pressure transducers and data acquisition modules and made sure we put them in a case in a way that the customer could access them if they needed to adjust or replace them in the future. Speaking of our pressure transducers, the ones that we've selected and the way that we've mounted them makes it so that they can be disconnected, removed, replaced, and reconnected in a matter of seconds. All of our tubes, hoses, and cables are all using industry standard connection types, and all of our electrical connections use panel-mounted receptacles so that the end user can enjoy a true plug-and-play, tool-free experience. We leveraged advanced 3D CAD modeling software and additive manufacturing technology to design lightweight, strong, durable components that our customer can rely on for many years to come. What you're looking at here is the clamping component for our rain shield. One of the customer requirements was that this case be operated outside with a potential sudden downpour. So we designed a canvas rain guard, and this canvas curtain basically has a loop sewn into it that receives a dowel rod. And then that assembly is clamped between two 3D printed pieces. You know, our best ideas aren't usually our first ideas, and this is a perfect example of that. This actually started out as a piece of Velcro. One of the things that our team has found to have been fundamental in the design process and realizing these types of improvements has been prototyping. We have certainly been limited in our ability to prototype in the recent several weeks, but fortunately we started that process early, and our team thought it was really important that we remain diligent in carrying that prototype forward and continuing to develop it. So fortunately right now we're able to present that prototype to you, and hopefully Zoom is going to cooperate. We've had some issues with this video over Zoom, but I'm going to share a video presentation of our prototype. So bear with me for a minute while I switch screens.
Good afternoon, ladies and gentlemen, and thank you for coming to our Capstone presentation. We're glad to have you here. My name is Mike. I'm with the Aerothermal Solutions team, and I'm going to be demonstrating the data acquisition portion of the aerothermal test set that we have. This is our entire setup right here. One of the first design choices we made was to have a two-case system. This is our power case. We're going to start off with this. We had to have a power case because the transducers and the DACs needed a dedicated power supply. This is not the actual power supply that we would go in the case. Unfortunately, because of the current epidemic, we weren't able to get the correct one. But the power supply would sit in here. It does have a fuse for safety, and it has a prop to hold the has our prop here to hold the lid up, for any rain or whatever. Cannon plug connects the cable, which runs over here, all the way to, this is our DAC case. It's a much larger case. The power runs into here, into the same cannon plug. This is our DAC chassis. This collects, this is the data acquisition chassis. It collects all the data from all the information that comes in, and then through this blue Ethernet cable, this comes over to the user will have their own laptop. This is the data acquisition case displayed in the inclement weather mode. We have a water-resistant tarp that connects inside the lid and comes down to protect the wires and all the components in case a downpour does come. Super easy. Just flip this up, open the lid for if the weather clears up or if you have to do anything inside. These are the props right here. Very adjustable. They store down, all the way down for storage, come right back up whenever you need to prop the lid up. Looking at the inside of the case, we have 3 fuses that line up with the 3 modules that are supplied from the power that run the pressure transducers. This is for safety mitigation. All of the pressure transducers are on these DIN rails right here. These these hoses go out to the rake and they bring in the data that the rake team is picking up from their sensors. If we look at one of these DIN rails, we'll pull it up. You can see that this is our pressure transducer. The good thing about this is you can pop this out, pull these right off with no tools and replace it if need be. We also have this wire loom under here that has all the wires, so there's really good wire management. There's no problems with getting wires tangled up. Easy to change out if need be. And all of these DIN rails come up just as easily. Now, aside from all of these components being easily changed out without tools, we also came up with a design to use a case insert. That way we didn't have to drill or glue anything directly to the case itself and interfere with the integrity of the waterproofing and dustproofing of the case. And the insert is easy to remove if it gets damaged anyway, so we can show you how we can pull this right out. Comes up, goes right back down. And it just adds an extra layer of protection similar to a phone case. The other aspect of the data acquisition is the thermocouples. So up here in the lid, we have our lid insert, which holds all the plugs for the thermocouples. And these are just like the bottom. There's no tools required to plug, unplug, to switch out these wires. All of these wires will be wired through and into this wire sleeve coming out. Again, proper wire management right back over here to the DAC chassis. These are the sensors that will be attached to the rake. At the top here, this is a pitot tube. It measures change in pressure, and this is a thermocouple. Measures the temperature, similar to a thermometer. So when air blows through here, it's going to come down to these tubes right here, and that's going to travel back into our data acquisition case, and that information will be relayed to the computer. We're going to show you a quick demonstration. We're going to blow some air into this pitot tube, and then you can see it operates off of an amperage change. So you'll see the amps change right here as the pressure changes. And that data would be compiled into our computer program and would show up on the laptop. Our software guys are going to demonstrate that a little later and explain to you how that works.
Okay, so let me jump back into the PowerPoint here. That concludes our data acquisition hardware part, and we're going to turn it over to the real wizards of our team, the software guys. Make this work.
All right, well, thank you, Daniel. Appreciate it. So we do have one technical difficulty. Our webcam is not working due to inclement weather and us being in a garage. So it'll just be audio for us. Of course, you don't need to see our face. The PowerPoint's the more important thing. So if Daniel can get that PowerPoint up, we'll continue on. All right. My name's Elijah Hayden. Thank you again, everyone, for being here. We really appreciate it. We're all very proud and excited of what we did this entire year-long project. I'm going to talk about what the software's role was for this project. Basically, from the start, we realized that there's going to be large amounts of data that was being collected at a fairly high rate. Also, many calculations need to occur at the same rate. This was obviously not feasible for manual recording or manual calculating. Therefore, it became apparent that we would need some type of computer aid with this project. We preferred something, obviously, that was going to be a visually aided software that would also be able to handle a large amount of data at the very high rates. Next slide, please. So the software that was used for this project was known as LabVIEW. We used this software for the collection and the processing of the data. For those who are not familiar with LabVIEW, LabVIEW is actually a visual programming language, which differs from most just code-based in the sense that it's more block diagrams and wires that do the coding. This allows the user a more graphical method for creating and for also using the programs. LabVIEW was a requirement by the customer due to how widely it's used over there at Cherry Point and also even further just in all FRCs for data collection. In total, at the end of this project, 14 unique codes were created that all come together to perform the necessary functions for this software. Next slide. So at the beginning of this project, we sat down and we realized we needed to determine what the software needed to do before we were going to determine how it was going to do it. So we sat down and we created something known as the software system overview. This is the architecture of all that software. We determined that there was going to be 4 main higher level functions for this program. Those are calibration, data, record, and display. Starting from left to right, the calibration first sends, it's responsible for sending calibration files to the data, which basically allow the data to make sense of the currents and the voltages that's being received. The middle one, the data function, is the heart of the entire program. The data function collects the data and distributes it where it needs to go. It also manipulates any of the data, so the user can make sense of it. Above that is the display function. This is the surface level function that controls the rest of the functions. If the data is the heart of the program, the display would be the head. The display function, as you can see with those yellow arrows, sends recalibration signals to the calibration code. It also sends collect data to the collection function, and it also tells the record function when to record. Basically, the display higher level function is the interface that the user will see. Lastly is the record function. The record function, as simply as it states, it's the function that records the data in an orderly, neat fashion that would make sense to a user so they could use that information at a later time. Next slide, please. So now we're going to do a quick software live demonstration for you. So Daniel, if you want to stop sharing, and we'll start sharing here. Sure. All right.
This is when you get nervous, right, guys?
Oh, yes. So this is where I would ask all the users to try to have your Zoom screen split in half, so where the left is the screen share and the right would be the person currently speaking.
So Eli, right now we see Nick Higgins with no video as the one speaking.
That's good. Yeah, that's what we want. We're about to turn that audio on here soon. All right.
So now, if you hear us, now that I'm speaking, you should be able to hear us and see the demo set up there of the over here showing the heat gun and then the pitot-static tube. And then this is the thermocouple that'll be testing the heat. So when I turn this on, what's going to be happening is it's going to be blowing hot air right here at the pitot-static tube, detecting that air pressure. And then this thermocouple here will be picking up that heat. So we're going to do it on low first, and then
all we see is
kick it
the
up. And
laptop screen.
sorry, say again.
We don't see the webcam. All we see is the laptop screen.
I see them both, Daniel. Make sure you go into gallery view and let Nick be the last person that talks.
Tell them that's not your web.
Yeah, so like Dr. Fortney said, you're going to go into a speaker view to where on the left side you're going to see the share window. Yep. Okay. And also we forgot to mention, if everybody can just double check, make sure that their microphone's muted, so that way you don't take over the speaker view as well. But yeah, so we're going to have right here the heat coming out. We're going to start on low heat first, and then we're going to kick it up to the high setting, and you'll be able to see that change on the lab view that Eli is going to talk about.
All right, thanks, Nick. Appreciate that. First thing I'm going to show you here is the GUI, also known as the graphical user interface that we've created for the user. The main panel here is all of the inputs. So these inputs allow you to stop the program, you can run the calibration, you can also record. Remember how in the previous slide I was talking about how the display function can call the other functions to perform certain tasks? These are the buttons that allow that to happen. So the user can stop, run calibration, they can record, they can also enter any file references that they need to. Further down, these are the display matrices that the user will be able to work with. So if I run this mock program, right now, since we weren't able to calibrate, since we don't have a calibration device, we are having the data send random simulated information. So as you can see, all these buttons here, we have columns C1 through C7 and rows R1 through R6. This allows the user to select the shape and size of the data matrix that they want to either look at and or record. So if they simply wanted a 3x4 matrix, they'll click the 3 rows that they wanted, the 3 columns they wanted, and the 4 rows that they wanted. And as you can see here, data is being thrown in there. Now we're going to show you some actual live readings from our thermocouple and our pitot-static tube further down here. As you can see on these two waveform charts and these indicators above. So let me just show you and kind of lay out everything that's going on right here. Can everyone see my cursor?
Is there anybody who can't see the cursor?
All right, I'll take that as a yes. Right here, this is the air velocity indicator. This is giving us the values of the air velocity in feet per second. This is the waveform chart that shows the amplitude of the air velocity versus time. Over here on the right-hand side, this is the temperature in Fahrenheit with another waveform chart that gives you the amplitude of the temperature versus time. Right now, we don't have anything running. So as you can see here, we have a slight resting error. Our transducers actually do have a zeroing procedure, so they would be able to zero that out. We won't do this for this demonstration due to it taking a little time to do that.
All right. So now Nick's going to go ahead and take over with the air gun.
Just going to kick it on low first, and you're going to see the airspeed go up, and then the temperature start to go up as well.
So as you can see here, as soon as you turn it on, the air velocity jumps up about 11 feet per second. This is clear jump right here.
Also, the temperature is starting to rise quite steadily to almost 200, 190.
Now we're going to kick it up to high, and you're going to see it jump up even more.
You can see the second peak right here. Velocity jumped from about 11 feet per second to almost 17 feet per second now. Temperature also jumped right here again. And it's about over 300 Fahrenheit already. As soon as he turned it off, you could see that the velocity dropped down to its steady state error of around almost 0, and the temperature now is slowly cooling off. So that's what we have to show for this. I'm going to now hand it off to the next teammate. Nick, if you, Dan, if you want to go ahead and share the screen now.
Okay, is everybody seeing the software live demonstration PowerPoint screen again?
Yes, we are.
Right.
Okay, so I'm Liana, and just to get sort of a good idea about what this project would have cost if it had been designed by FRC instead of students, we went through and we did a whole cost estimate on what exactly it would cost to design and produce these test kits. So we went through and we did a cost estimate for the individual higher components. And when it says on the screen, one complete test kit, what we mean is all components needed to perform a test cell verification. So for the intake rake, we needed 1 per complete test kit, and the total cost per test kit was $59,000. For the exhaust rake, we needed 1 per complete test kit, and the total cost would have been $147,000. The intake data acquisition case, we needed 1 per complete test kit with the total cost per case of $30,000. And then the exhaust data acquisition case, 1 per test kit as well, with a total cost of $30,000. From there, we move on to the power supply case. The power supply case, we needed 2 per complete test kit, 1 for the exhaust data acquisition case, and then 1 for the intake. The total cost per case of $1,600, and a total cost per system of $3,200. For the connecting hardware, we needed 2 per test kit, 1 to go from the power case to the data acquisition case on the inlet, and then 1 for the exhaust as well. Total cost per connecting hardware for the case set is $1,400, and the total system cost was $2,800. When we say total cost, what we did was we took the price for the commercially available parts that we specified for purchase, as well as the materials and labor costs needed to manufacture the locally manufactured parts. So that's how we arrived at those numbers. Now, also on top of the costs needed to actually produce those parts, there's an engineering cost associated. So with our 2 design teams of 6 engineers each, total of 12 engineers, we worked about an average of 16 hours per engineer per week on this project, for a total of 33 weeks or around 6,400 hours. At a pay rate of about $150 per man hour, which we got from FRC as the average engineering rate, the project engineering cost would have been around $960,000. So the total project cost for the rakes combined was $206,000. All of the data acquisition components, $66,000, and then you add in that engineering cost of $960,000. The total project cost would have been $1,232,000. So it was a bit surprising for us to see those numbers coming at it and going, oh well, we're students, you know, we're designing something. It's not going to be a crazy cost. When we tallied up those numbers and we looked at that, it was a little surprising for us to see. So that kind of gives you a good idea of real world. what a design like this would cost to produce and the impact that could have on a company. So that's it for our presentation. We know that things have been a little crazy. We really appreciate you coming. This format has been new to everyone. So we appreciate you taking the time to come here, taking the time to figure out how to use all this software. And then we wanted to open it up and ask anybody if there are any questions that you have for us, any comments you have on the design. We'll answer anything we can.
Leanne, I'll jump in here and give another chance for questions also. Thank you all, you did a great job. One of the other partners that I wanted to acknowledge was Cherry Point. They have given us these capstone design projects every year. So this group of 12 now marks the 46 graduates that we've had from this program. And Cherry Point has supported us immensely through all of that. And Patrick Townsend is here, and Patrick really has been our port of contact on all of these projects. So Patrick, I don't want to open it up to you to see if you want to say anything, any comments you want to make to the group.
Yeah, so you kind of already mentioned this group's already been through a lot with the hurricanes. What you failed to mention, they've also had to deal with Dr. Dave's first year of teaching. So they a little bit of a learning curve for him and the group there too. Really proud of this group. They had to go through a lot, like you said. And for all the visitors on the call, you may not realize the amount of work that actually goes into a design project like this. So all the models you saw, the calculations, all the thought behind this was condensed into an hour presentation. But like you saw, 6,400 hours of engineering went into this. We try to give these teams as real projects as possible. This is a real need. The function is to ensure that the engines we produce and that are flying over your rooftops and protecting the country are safe. So I think they came up with a great design. They worked through the whole process. I don't really have much more to say. Just really proud of them. Good job at adapting.
Thanks, Patrick. There were several other engineers that worked on this design team. Anything any of you guys want to say, or anybody from Cherry Point?
I get to wear my Cherry Point hat again. No, I just think the eye opener, right, was the amount of effort that goes into these. Like Patrick had pointed out, Leanna pointed out, that this is real, right, for the community. As the community steps in and these jobs are available, and the portability of the training to Cherry Point, it's a win-win situation. So I think this is a great example of that.
Great. Anybody else?
Yeah, actually, I would just like to mention our NC State local staff, Dr. Fortney, Michelle, and Miss Susan. I think on speaking for all of us, these three have really been just a blessing to, I know me, and I think all of us can agree, the dedication, the amount of work they put into this program and helping us through these kind of, situations like the hurricanes and making sure that we stayed connected and that we had everything we needed to get the job done. We really appreciate that. We look at Miss Susan as kind of a grandma or a mother, aunt. How about an aunt?
Don't say grandma. That'll get you.
That came out wrong. But
as a young mother,
a cool older sister who holds it all together.
Yeah, we can always rely on Michelle. Anytime we didn't read an email from NC State or we forgot or missed something, she's always there to have our back. And the level of dedication that Dr. Fortney puts into everything that he does is really what makes this program kind of run as smooth as it does. So just wanted to recognize you guys.
Thank you, Daniel. I think we're really proud to be associated with you guys.
Bill Tom Brunton. It's been interesting to always watch every year there's a capstone, or every time there's been a capstone project, how interesting and how dedicated these students actually are when they actually start doing the research and applying it, and the benefit that it's actually producing, not only for FRCEs, but also when you think about your program and the partnerships that you have with FRCEs to pay them. To me, it's just a testimony of all the hard work that's been placed throughout NC State, Creighton, and FRCEs, and really my hat's off to each and every one of you. I think you all did a great job on this project. It was interesting, it was enlightening, and I learned a lot, so thanks a lot.
Cool, thanks, Wally.
Bill, Tom Broughton here. I'm curious, how did the students get assigned to the different groups? Was that by their choice, or someone at NC State decided who would play which role?
So Dr. Dave and I put our heads together and split people up. So they were thrown into their teams. They didn't get to pick.
Yeah, this is probably a good point we didn't really touch on. Most, over the 7-8 years I've been helping out, we've had fairly small teams, 3 to 4 engineers up to 7 or 8. This was 12 engineers trying to come together, each having different roles, and then putting their presentation, their papers, and their projects together. So it added a new wrinkle this year, which we really haven't had in the past. We've had, a couple smaller groups, but to the level that this group's had to integrate amongst themselves, it was a different challenge, and I think they did pretty good with that.
Yeah, definitely. Thanks, Patrick.
One more question on the fiscal part. Sometimes a customer will tell you, design this within this fiscal constraint. Here's the dollars you can spend. Was this team completely unconstrained? They could do whatever they wanted and then just come up with a cost at the end?
We were told that there was no set budget. But what we did when we were going through is if there were multiple components or materials that offered the same level of either structural integrity or performance, we always went with the cheaper option to try and keep the cost down. But we were not given a set price point. We were told to just design and then figure out what it cost at the end.
Thank you.
Maybe I missed it, but what did FRC say at the end of the project? Because if I recall, the students saying that there have been problems with previous test kits. So what was the overall evaluation from FRC if they gave one at the end of the project?
So the issues we had, this is an actual project we had. The first design we came up with, we had about a month to come up with it and implement it. So the design we currently have and utilize is probably, 8 or 9 years old. So it's outdated, and the portability and interoperability of all the components is not there. So that's why when we gave them this project, we wanted them to focus on something that's easier to change in the field. So we're definitely going to look at implementing this. It's kind of a project that comes up and then you need it. So we usually don't know 3, 4, 6, 7 months ahead of time. It's usually, hey, we're building this test cell. We need to go correlate it or check it. So it'll be something we're going to keep on the shelf, and then we'll implement it when we have that come up.
I just wanted to say thank you to the staff and the students. I always enjoy these presentations. They're wonderful. Thank you.
Yeah, and we really appreciate all the community people coming. It is a great partnership. We do everything we can to let people know about it. We're really proud of these students, especially in these crazy times we have. We have 12 graduates. All 12 have jobs. 11 of them are staying local. 10 will go over to Cherry Point. Daniel is at Tandem Lock. And then Caitlin is going back to the Virginia area, and she has a job up in that area. So I'm really proud of them and just the fact that they do all have employment even with these crazy times. So thanks for all the community support that makes this program possible. Okay, great job, you guys. Thank you very, very much, and appreciate you guys joining us. And I'll let you all leave, and then I'll close the meeting when everybody's gone.
Yep. Thanks again, everybody. This was great.